Okay, are we happy to continue? We're ready to get the next part. So there's book one. Again, just say do the questions in your own time over the weekend. Won't take too long. And then hopefully by later on today, Mr. Sanjeev will have some questions that I've sent him for you to hand out, either by email or actually pick them up there at NAT itself. Okay. And again, the questions I've got, they're a bit mixed up, as they're not necessarily in the right order. You won't be able to do all the questions yet. We've not covered book two, but the answers are at the back of the sheets. But the best thing to do, try the questions first, and then check your answers at the back. But the answers are there for the questions as well. Okay, they're just open questions. So hopefully that will help you with your revision for your exam as well. Okay, we're going to move on to part two. All right. Now, as I say, this one slightly more in depth, and a bit more going on with it, and a few more technical pieces to start with. We're going to look at pitch control, synchronization, or synchronizing, synchrophasing as well, ice protection, maintenance, and then finally we'll look at storage and preservation. How we're going to look after these propellers once we take them off. Okay. So chapter one, we'll look at propeller pitch control. Chapter two, synchronizing, synchrophasing. Chapter three, propeller ice protection. Chapter four, propeller maintenance. And as I said, the final one will be propeller preservation and storage. Okay, so quite a few bits to get through. Oh, chapter one, propeller pitch control. How we actually make these constant speed propellers move. So controllable pitch propellers. Now, the pitch propellers, let's get rid of this before I forget. Okay, that one. There we go. Back on. Okay, so the controllable pitch propellers make it possible to adjust the blade angle of a propeller in order to maintain the best possible performance. So it doesn't matter what the pilot's doing, what power he wants, this constant controllable pitch ones will adjust accordingly. So at takeoff, the propeller is normally set to a low angle, so we get high speed, high torque, so we can take off at a high rate of climb. Okay, maximal power available, so it's not struggling. Again, in a car, you wouldn't take off in fifth gear in a car, you take off in first gear. So get high power to get yourself going. And same for aircraft, we don't have gears obviously, but we have the angle of attack, okay, the blade angle. So there you go, the fuel range position. So from taxi, you've got the ground fine stop, is almost pretty much straight up and down, but we've got roughly about +4 degrees there on average. Then we go to the flight fine, which is pretty much ready to go, about 17 degrees, all the way up to about 27, and even to feather, almost 90 degrees, you know, okay, 85 degrees there, in line with airflow. And likewise, we can come back the way to reverse thrust, about -15. Okay. Again, we'll cover these as we go through the book. So, short after takeoff, angle will be increased slightly to prevent overspeeding, because once, remember, back to book one, as we get movement of the forward speed of the aircraft, the angle of attack will decrease. So to maintain that angle, we need to increase more power or more RPM, and that will maintain the angle of attack. Okay. When the aircraft has reached cruising altitude, we don't need that high speed. We can chill down a little bit. Okay, the propeller can be adjusted to a comparatively high pitch, so quite a large angle, so we can sit at the cruising ability of the aircraft. Okay. Automatic pitch control, usually carried out again by constant propeller speed, RPM, whereby propeller blade angle is automatically adjusted to maintain. So the pilot doesn't have to worry about it. If it's automatic, he can set the power he wants, the engine RPM, the propeller control, and that will maintain it irrespective of what he's doing. So, achieved by incorporating constant speed propeller, obviously. And we can have what's called a single acting propeller, and we have what's called a double acting propeller. And this is to do with oil pressure either on one side or double acting of oil pressure on both sides. Okay, let's see how to do that. Now we can also have a moving piston, which moves the propeller, or we can change it, the piston stays still, we can actually move the cylinder instead of the piston. Again, why? Because they can. That's the way the designers do them, some of them. And obviously with our ones, we use the constant speed unit. Okay. And maintains, there's a governor in there which maintains all this. and also the propeller control unit. So a version of those for CSU and one for the PCU. Which one was for the piston engine? Which control unit was for the piston engine? Anybody? Was it the CSU? Yeah. C for P and P for jet engine. Yeah. Good.
P for turbo.
Yeah, turboprop. The turboprop was just a jet engine with a propeller on it. Yeah. So in variable pitch propellers, in a typical variable pitch propeller system, the RPM control lever is usually connected to your PCU or CSU, depending if it's a turboprop. So the PCU is basically a CSU, exact same thing, with additional features to meet the requirements of that particular system. So looking at them, they look pretty much identical, but there might be a couple additional features possibly. So to give constant speed control provided by either PCU or your CSU, it will obtain the best performance from the aircraft engine and also the propeller. It will offer minimum rotational drag during starting and acceleration from ground islands, so it's all automatic. Typically provided by ground fine pitch stop, which can be fixed or withdrawn. And we'll look at a few variations of those later. It also limits the degree of fine pitch available during flight. Typically provided by the flight fine pitch stop, which again is withdrawable. Requirement is to incorporate safety features. Yeah, it's got to be safe. Kit for engine, so we don't overspeed the engine. The propeller and control unit failures that could cause, obviously, damage and drag, etc. We don't want it failing in such a way that if it fails in a fine position, that's going to cause a lot of drag on possibly a twin engine aircraft on one side. We don't want that. We want to fail it in a fair position if something goes wrong. Usually provided by what we call hydraulic pitch lock, an electro hydraulic stop. It could be an auto feathering system. And that's the three sort of main ones there: hydraulic pitch stop, electrical hydraulic stop, or an auto feathering system. So just in case something goes wrong, one of these should work or kick in and put the propeller in a feathering system. So to allow manual feathering on feathering when required, usually provided by a feathering spring. And that's more for a single acting type propeller system. You'll have a cockpit HP cock lever. So the HP cock lever provides your fuel to the engine, and also as part of that, you can incorporate that to, as you shut down the fuel to the engine, that will allow the automatic system to put to the feathering. A feathering switch, so an electrically operated hydraulic type system. And a feathering unfeathering pump. As well as an oil pumps in the engine, we have a feathering pump in there as well, just to give a bit of assistance. And counterweights which act to oppose CTM. What was CTM again? What does CTM stand for?
Centrifugal twisting movement.
Yeah, twisting a turbo. And which way did the blade try and move? Was it to a coarse position or a fine position?
Fine position.
Fine position. So we've got counterweights in there to help prevent that. Okay, and depending on how many weights on there will counterbalance the force of the centrifugal turning moment. And help coasting blades and the feathering spring to move the propeller to feather. To allow manual feathering when required, again, usually provided by feathering spring, cockpit lever, as we saw before. I'll take that slide out. That's a duplicate slide. I do apologise. A constant speed type of fact, just give me 2 seconds because I will forget this if I do it wrong. Let's just get you back in there. Just give me 2 seconds, guys. Don't have. Yeah, both the same there. Just take it one out. Sure. Start again. Okay. Save that one. I just noticed that was a double slide. I'll take that one out, save it before I lose it. There we go. Back to it. Thank you. Right. Yeah, if the RPM propeller tends to increase, the governor senses the increase and responds by causing propeller blade to also increase. Also, propeller tends to decrease. Again, the governor will cause a decrease in propeller angle to maintain constant speed. So if it senses the propeller starting to slow down, In other words, we've got too coarse a pitch, we need to speed up, too much strain in the engine, it will fine off the angle, allow that to speed up. So it's all done automatically. Propeller governor must be driven directly or indirectly from the engine so that it can't sense the engine RPM. That's what's there for. It needs to know what's happening in the engine RPM. So if the engine's starting to struggle, it means, right, okay, we need to get the blade going faster, so we'll fine it off a bit. Now, it can be geared up or down, but it must be fixed proportion to the engine RPM. So depending on which method it's been designed to, up or down, it has to be proportional to the engine RPM. Governor must also be able to accept oil from the engine supply and increase the pressure to a value that also will cause rapid propeller response to maintain that constant RPM. We don't want it reacting a few seconds later or lots of time later. It has to be pretty much instant. That's quite important. So, constant speed propellers, the governor must be designed, the direct oil pressure to or from propeller, so the propeller blades can't be changed. So, as your constant speed, moving the propeller, oh, change that, sorry. So, you've got your levers there, okay? So, your speed control, moving the propeller control forward allows the blades to take a smaller bite of air, okay? Drag increase, and engine speeds up. So, in other words, by moving it forward, it makes a finer position, a smaller blade angle. Again, what you must watch obviously is keep it within the green zone. We don't want to go in the red zone, otherwise we're going to overspeed the engine. So again, if you've got a constant speed propeller, moving that control obviously down to the experience of the pilot to make sure he doesn't blow up his engine. So it says there, it must be constructed so that the pilot can adjust it in flight and select the desired RPM. Okay, and again, likewise, you bring it back, pull the propeller rearward, forces the propeller blades to take a bigger bite of air, in other words, more thrust. But again, that also depends on the flying conditions and how fast the aircraft's going as well. So fine position going forward, pull the lever back, and you'll get a coarser position. But again, you have to make sure you've got enough engine power to compensate for that one. Okay, now the pitch change devices for constant speed propellers include electric motors, hydraulic piston cylinders, like we saw before, springs, centrifugal force and counterweights, etc. Again, or a combination of all those methods. Again, your PCU or your CCU maintains selected RPM as normal, again for changes in flight conditions without the assistance from the pilot. That's the main thing here. It takes the load of the pilot, okay, and yourself, you're doing power runs and stuff as well. But you need to function as an engineer. You have to test all these systems to make sure they are actually working. So in that condition, optimum angle of attack for propeller blades will be selected at all times. Blade angles can be changed, as we saw before, as much as 110 degrees, which allows the propeller to be feathered and also be used as a power brake, as I said before. And just to recap, I said before, PCUs are generally turboprops and CSUs are with pistons. So again, the CSU, just to recap, again, all controls it. Most engines produce their maximum power in a narrow RPM band. In your CSU, your PCU, it's said to be an aircraft with an automatic gearbox, is that to a motor car. So basically, a car, you don't have gears in automatic, this works on the same sort of principle. Okay, it will maintain the right gear for your aircraft, although we don't have gears in the aircraft, like an automatic gearbox does on a car. And so you want to go faster, it will select the right selection for your right amount of torque. Engine can be kept running at optimum speed, no matter what speed the aircraft is doing flying through the air. So it's constantly sensing RPM. If it senses a drop, it will increase the propeller speed by fine angle off, and likewise, if it's going too fast, it will increase the angle. Of course, with the CSU and a piston engine, aircraft has another benefit. Allow designers of aircrafts to keep ignition systems simple. An automatic spark advance seen in motor vehicles, I don't know if some of you might be ex-motor mechanics or working your own cars or motorbikes, is much simplified in aircraft engines. But basically, piston engines in aircraft are piston engines with wings. They're very, very similar. If you ever do a Module 16 course, you'd be surprised how very similar it is to normal cars. Older ones, that is. So two methods are used to vary the pitch of propeller. Engine oil pressure, so using a hydromechanical type version, as usual mechanism only, commonly used in commercial aircraft. Electrical pitch control are usually for the smaller aircraft. We can use the oil pressure in the large aircraft, big supply, but for small aircraft, rather than take a bit of oil from the little engine, we can use little electrical motors instead. So general governor components, the housing, again, strange enough, an aluminium type cast, and again light and strong at the same time, composed of 3 primary sections or of 1 basic section. So 3 primary sections are, this is a really hard one, so hopefully hang in there. Head, the top of it, contains the pilot's control components, will be at the top of the governor, strange enough. The body is in the middle, contains the sensing components, and that directs the oil flow exerted to the pressure regulation unit, which will then move your propeller accordingly. And then at the base, well, that's at the bottom, that contains a mounting surface we can bolt to the reduction gearbox, and that joins onto your engine drive system. So a little spline coming out there into your gearbox and contained to your drive system. So it can actually spin the governor. So your head, your body, and your base. Okay, and there you go, there's a little diagram there. So as you can see, there's the head, there's your body, and there's your base. Okay, nice and straightforward. I mentioned the word single acting propellers, and basically you've got oil pressure one side of a piston with a very large spring behind it. Okay, and this can be 2 or 3 bladed, constant speed, and fully feathering propeller. Hydraulic oil pressure from the engine to the governor is by either CSU or PCU, as normal. Directs the blades to a fine pitch. It will increase RPM obviously. So the greater the pressure from the oil, it will push that propeller blade into a fine pitch, which is pushing against this big spring that's in there. So the feathering spring and counterweights direct the blades to the coarse pitch. So decrease RPM and the feathering as required. So as the oil pressure decreases, the feathering spring will overcome that pressure and move the blade into your normal feather position. Okay. So as long as you've got oil pressure in there, and depending how fast the engine's going, will determine how fine that blade is. Once we lose oil pressure, i.e. shut down or emergency, then the spring will take over and turn the blade into your coarse or feathering position. Again, usually cast from aluminium and may be compressed of 3 prime sections or 1 basic section, just like we saw before. The major components of a single propeller are in here: cylinder, okay, so the housing, which will have the piston in there, so the actual external part. You'll see the big spring in here as well. Piston, so there's the piston there, which is attached to the rods, which is attached to your propeller blades. You'll see through the middle here the oil supply. Oil transfer tube. Okay, so there's your CSU oil come through the transfer tube. And your pitch change link rods. So these rods here, the brown ones here, that's your pitch change link rods. Pitch pins, okay, with the actual blade sit in, and there's some sort of pitch change spider. And the spider is just a housing that holds it all in as well. And you'll have what's called a ground fine pitch latch stop. So it actually locates in there, actually stops it from moving out there once it goes past that point. The engine is not running, the latch stop mechanisms prevents the blades from moving to the feather position. Now it'll stay in the fine position, ground fine position. All right. You can just see here, this point here, it's hard to see in the diagram, probably see easier in your book, to be honest. A little valve that moves across. I mean, there's no pressure, the weight holds it down, it will latch in position. The only thing that will move that out of position is centrifugal force, or indeed potentially oil pressure, depending on the system. Okay, so a little latch stop just keeps the blades in a sort of fine position. When the propellers are taken correctly and after a successful start, the centrifugal force is sufficient to lift the weights out of the way. Now the weights, they can be oil pressure, it can be spring pressure. It could be a spring behind that latching mechanism which pushes down, which stops the locks from coming out. But once we get enough centrifugal force, the latching mechanism will push against the spring, which will allow the connector to disengage and then allow the propeller to move accordingly to a far more coasting position. So there's a close-up of it. So in the previous diagram, there's the actual pin, and you see it's actually held in position, these little latching weights, and a little spring there as well. So once we get centrifugal force, these will move up or down in this case, and that one there, out of the way, and that will allow these fine pitch latch stops to move out of the way, which will allow the propeller to move to its normal position. Okay. So then again, there's the latch weights. You can see there, I don't know if you can see well in the computer, the latch is touching the actual lock. But here, as we've got some force going around now, the latch have moved up out the way in this case and down out the way. So that allows this latching point, the propeller in effect is now free to move, depending on the oil pressure which is in here. We'll get an oil feed through the hollow tube into the front there, and that will go against the piston. And this is your cylinder, the blue part's the cylinder. So there'll be oil in this part here, pushing against the piston, depending on how much pressure is in there, depending on the speed of the engine. Okay, so I can see here at the moment, once they've moved out of the way, the feathering spring, which will be back here somewhere, is now pushing this piston forward to allow the blades to move, and I'll go into the feathering position. So fully forward, you can now see that the locking pins are fully disengaged, okay, because as it's spinning around, the latching locks have spun out the way. So the spring has pushed this piston, the screen part here, fully forward. We're now in the fully, as close to feather position. Once we get oil pressure on this side though, that can start moving back away into a finer position. But initially, on a typical centrifugal latch, it will disengage and go to the feather position. The aircraft we've got in the hangar back at Scone, up in Scotland here, we put them into the fine position. We get the students to actually get what we call wooden paddles, which locate onto the propellers, and they take the tension. We physically move these locks out of the way, and then by gently allowing the pressure of the spring to move the blades into the fair position. If you don't hold on to it, the spring will move it very, very quickly, and you'll hurt your face. We usually have 2 or 3 people on there doing that at one point. Okay, so be very careful if you're doing this yourself. Obviously, you shouldn't be doing it yourself. That was for single acting. Now double acting. So single acting is, as I said before, spring pressure will overcome oil pressure if there's no oil pressure. But once we get oil pressure, we can push against the spring. Double acting means we've got oil pressure on both sides of the piston. Okay, and just to make it confusing, they operate slightly different. Okay, I'll show you what I mean as we go through. So double acting type propeller, similar to single acting set, we have closed at both ends. You've got oil pressure both sides. There's no need then for a feathering spring. We're using oil pressure on one side and oil pressure on the other side. Okay, so both sides of the piston. So 2 types of mechanism might be used to connect the piston to the blade roots. One is the pitch change links, a rod and a spider, are connected to the piston, pass through seals in the rear of the cylinder, and are connected by pins at the individual roots. Again, you'll see a diagram in a minute. And there are 2 main types of piston link latch change mechanism. Bit of a mouthful there. First one is the moving piston, just like a normal piston you saw before. Or we can change that. We can actually have the cylinder that moves. So the piston stays still, but the cylinder will move outside the piston. Does the same job, but it's just the cylinder moving instead of the piston moving. The piston stays stationary. Again, why? Why not? Again, it's up to the designers, unfortunately. They decide to do it that way. So a moving piston, just like a normal piston in an engine, cylinder and piston are mounted on the front of the hub. The piston is linked to the blade roots. So that the piston moves, the blade angle will change. So this time the pistons, whatever the piston does back and forward, will change the rotation of the blade by the linkage. Small aircraft propellers may use a single acting mechanism, and larger tend to use the double acting. The Jetstream aircraft is a twin turboprop, free turbine, and that's the single acting one that we've got. Oil pressure passing through concentric oil tubes is used on both sides of the piston to change the blade angle in this case. So there we've got a moving piston. So what you can see here, we've got the blue oil pressure and the red oil pressure. The blue is representing the fine pitch, and in this case, the red is representing the coarse pitch. Now, to make it confusing, why they've done it this way, why not change to keep it simple? On the single acting piston, remember, instead of oil pressure in here, there'd be a big spring. And if the big spring moved the piston forward, that went into the feathering position, a single acting one. But just to make it confusing, on a double acting one, this time it puts it to the fine position, just to make it a bit more confusing. Okay, so instead of a spring this side, we've got oil pressure, which moves the piston forward. This time on a double acting, it moves it to a fine position. So when the oil comes to the front of the piston and moves the piston back the way, that moves it to the coarse position. So double acting, again, to make it confusing, does the opposite from a single acting. Why? Again, that's the good old engineers, designers, just to make it that way. All right, so single acting, feather spring moves the piston forward, goes to feather. Double acting, the piston goes forward, it goes to fine position. Okay. Anybody confused with that one? Yeah. Yeah. Basically, this piston here will move back and forward. Yeah. If the piston comes towards the front here, the propeller blades will go into the fine position. Okay. And then if you've got more oil pressure on the front of the piston, which will move the piston back the way, that will move it to the feather position. Only on a double acting piston. Okay. On a single acting piston, if the same piston goes forward, it will go to the feather position. But on a single acting piston, we've got oil pressure in the front and moves it back the way, it will go to the fine position. So in other words, a single acting piston does the opposite position of propellers to a double acting. Okay. That makes sense there? Again, why not just change the oil supplies around to keep it the same movement? Hey ho, that's the designers for you. All right. So piston goes forward in double acting, that goes in a fine position. Piston goes back the way, it goes to feather position for a double acting piston. So double acting is oil pressure this side and oil pressure at the back of the piston, hence why it's called double acting. Go back to your single acting, just to show you again. The single acting. Okay, so instead of oil pressure, there's your piston there, like we saw before. We've got a spring, so there's no oil pressure. We've got oil pressure coming through the center of it and then filling this area up here in front of the piston. So if the oil pressure increases, that will push this piston back the way, compressing the spring, which will move it into a fine position. But once we lose oil pressure this side, like we shut an engine down, this big spring will push the piston forward, and that will turn it into the feather position, which is the complete opposite angle of a double acting cylinder. So there's that piston. Okay, so what I'm trying to say here, we've got two oil pressures, one on the back of the piston and one on the front of the piston, indicated here by the red and the blue. Okay, but for some reason the designers made it that it does the complete opposite version of a single acting one. Okay, again, we'll cover this a few times just to get your head around it. So there's no spring in double acting, it's purely oil pressure, which will move the piston forward or move the piston back the way. Okay, that's all that's happening there. That's a moving piston. We can change it by leaving the piston staying still. At this time, we'll move the cylinder instead of the piston. Does the same job, but we move the cylinder instead. So very similar to the piston type. But in this time, the propeller, the piston is fixed and divides the coarse oil and the oil pressure supplies. Oil pressure is fed to one side of the piston, again, just like we saw before. On this side, oil is returned to the CSU or the PCU through concentric oil tubes. Oil pressure moves the cylinder, which has been linked to the blade roots, and the blade angle. So it looks identical, all right? But this time, all right, we've got the oil coming this side, we've got the blue, the coarse is the smaller through this green tube. So the coarse oil this time goes on the front of the piston. The fine oil, this type, is on there. Okay, that should be red in there, not blue, sorry. So this time, it's the outside part that's moving, the cylinder, not the piston. Okay. So you can imagine the coarse oil there, that goes through the middle, which comes out down. So when the oil pressure builds up here, instead of moving the piston, it actually moves the cylinder. So the cylinder is going to come forward. Okay, so the cylinder comes forward, that's going to go into the coarse or feather position. If we build oil pressure in here, that's going to move the cylinder back the way, which will go into the fine position. Okay. You can see there the arrow is indicated there. So as it goes round, it's coarse this way or fine that way. It's just a different way of doing the same thing. It's the cylinder, the outside part here, which is moving instead of the piston. This time the piston stays still, become oil pressure coming through the middle, oil pressure on the inside, and whichever one's the highest will move the cylinder forward or the cylinder backwards. Okay. Just a different method of doing the same job. That's all. So the cylinder moves forward, we go into coarse position. If the cylinder moves backwards, we go into a fine position. I've not changed that slide. That should say hydromatic, not hydromatic. My apologies there. I'll have to change that.
Fine
So again,
fine pitch oil is used only for moving piston.
say again?
Fine pitch oil is only used for moving piston or moving cylinder.
This is still classed as a double acting system. It's double acting because we've got oil pressure on both sides, one for the coarse and one for the fine. On a single acting, you only have one oil pressure system, one oil system, and that's on the front of the piston. Okay. On a double acting one, either the piston that moves or it's the outside cylinder that moves. Again, still using two oil pressures, either front of the piston or the back of the piston. In this one, the piston doesn't move. It's the actual cylinder, the outside part, which will slide forward or slide backwards by oil pressure. The previous one looks exactly the same, except it's this yellow part here, the piston, like in a car, that will move back and forward. The cylinder won't move, that's just containing the oil. The piston will move back and forward for the piston version, but for the cylinder version, it's exactly the same, except it's this part here, the outside part that moves. The piston, in this case, stays still. This is a moving cylinder, but the one before that was a moving piston. So it's the same job, except it's the cylinder that's attached to the propeller, whereas on the piston one, you can see there the rods are attached to the piston, okay, which is attached to the propeller. So that's a piston moving piston one, changes the angle. There's a moving cylinder, it's a cylinder it's attached to the propellers, which moves the angle. Okay, still classed as double acting because of oil pressure in the front face of the piston and the rear face of the piston, behind the piston here. It's the two different oil pressures going on. Okay. Just change that a minute. Give me 2 seconds, guys. Alright, so we're starting with a piston. Why is that still romantic? I'm just going to quickly change this. It's probably saved the whole. Yes, it is. I don't know why it hasn't saved. Just bear with me 2 minutes. Okay. So I'm just quickly changing the slide here. Just notice it's not spelled correctly. In fact, I'll change this after I've done the lesson. I'll make a note of this. I thought I'd saved it. Okay, back on this one. Hydromatic, not hydromantic. The dome is stationary cylinder. The piston is a U shape to contain a pair of what's called coaxial cylindrical cams. Outer cam is fixed to relation to the hub, and the inner cam is free to turn and operates a bevel gear, like we saw before in the gears, which meshes with the bevel gear segment to the blade root, so it changes the angle of movement. So shafts and rollers transfer piston movement into rotational movement of the inner cam. Now I might highlight these ones. We call them dog legs because they look like a dog leg. Slots in the cams are cut in opposite directions to double the movement of the inner cam. We'll see a diagram in a minute. Cam rotation to the blades, to the bevel gears to produce a pitch change proportional to the piston movement. Okay, so there's your propeller, there's the bevel gear on that side, and here's a bevel gear on the actual movement. So again, we've got oil pressure and we've got governor oil pressure. Now, depending on which one's biggest, we'll move this rod forward or move it back. Now, the rod doesn't go up and down, it moves just forward and backward, okay? Now, the dog leg here, hence why the dog leg type shape, as this got a roller on, it's like a little wheel. That will push against the surface here, which will rotate this, okay? If this green rod was to go back the way, it's going to push on this surface here, which will rotate this towards my screen, okay? Likewise, if the green rod goes back the way, it's going to push on this upper surface, which will make the cog turn the opposite way, all right? So if this was going that way, okay, then this would rotate along with it. Now, depending on the pressure, we'll move it to a fine or a coarse position, depending on the pressure in the servo, of the governor pressure, and depending on the pressure of the engine oil pressure. Okay, that's a geared or what's called hydromatic. So it's a cam, we call this a cam roller, which will go into the surface. And again, it will stop there, and it will stop there, the maximum and minimum points of fine and pitch. Now, in this diagram here, it's got a low pitch going that way. So in other words, if I want to go to lower pitch, I want to rotate it towards this side of the screen. I'm going to have this rotate towards me. So to do that, that means that this piston is going to go back the way, which will push down on this face, and that will rotate it towards me in this direction. Yeah, and that will spin the propeller blade in the direction of that arrow there. So in other words, engine oil pressure will have increased, okay, pushing that back, which will make that go to a lower pitch. Okay. Again, the governor is going to sense this and try to overact that depending on what's happening with the aircraft forward speed. But at the moment, we're just showing that higher oil pressure means we've got a lower pitch. And again, just showing you the geared or hydromatic components. So there's your governor, your PCU or your CSU, depending which version it is. There's attached to the gearing, okay, and there's small gears inside there as well. And eventually, whatever's happening on here, all right, you can see, now we'll try and find, it's hard to see in the diagram, you might see it in the books a bit easier. Let's just check the page number. Let me just check. Page. Yeah, it's not too clear, so it's not too bad in the page actually. Page 18. It's the same what's in your page. This is your hydromatic one. You can just see the cam rollers there. It's quite hard to make out, but just be aware the rollers are there. They'll be side of track. So again, you've got oil pressure one side, oil pressure the other side, and it'll go back and forth. Unfortunately, we've got one in the hangar I could show you, but again, we're not in the hangar, so bear with us. Okay, but again, it's a double acting system, oil pressure one side, oil pressure the other side. Instead of levers going back and forward, it's a cam on a track. All right. That's exploding. Now you can see there's a same diagram in your book. There's the dog legs, so where the rollers would sit in. All right. So depending on how much going forward or backwards, will rotate eventually the gear as it goes. So it's spinning backwards and forwards. When the piston goes backwards and forwards, it's rotating the gear because of the roller bearing on the cam, or the dog leg as we call it. Okay. All right, so that was the cam one. And then for small aircraft, we've got electrically operated propellers. And quite simply, electric motor, which will turn a set of gears, usually some sort of reduction gears. We need the torque because we try to move all this big amount of metal, it's going to be quite hard. Okay, so we'll have an electrical gear, some sort of reduction gear onto your bevel gear, which then will rotate, and again rotate the propeller blades. So other types: variable pitch, hub mount in the front, individual blades into the hub, and the pitch change mechanism is fitted to the front of the hub. All right. So what I'll do, we'll just finish the section off and go for a break. So, however, a bevel gear through the gear train with a very high reduction ratio. We need a high reduction to get the power from the starter motor. Same as a car. If a car has a very high reduction, because you've got to try that big, huge engine, well, if you do it one for one, it won't do it, it'll burn the motor out. So we need lots of power from the starter motor to turn your engine. In this case, we're turning a propeller blade. Driving bevel gear, output gear, the train meshes with the bevel gear at the top of the blade. You can just see that there. So the starter will be spinning this bevel gear through a reduction gear, which will eventually rotate the gear of the propeller. So the electrical power of the motor is provided by your brush and your slip ring arrangement at the rear of the hub and your disc. Motor brake is provided to prevent overrun and normally consists of 2 friction discs. One fixed on the rotating motor shaft and one keyed to the stationary motor casing. The brake is applied or discarded just like a car. I keep using a car reference, but it's the same principle. By spring pressure and released by means of a solenoid whenever a pitch change is initiated. Some electrically operated propellers are controlled by an engine-driven CSU or PCU, and switches are also provided which enable propeller pitch to be controlled manually. And finally, just before we go for a break, that shows you some of the components. So CSU is similar to those fitted hydraulically operated levers, but the governor valve in this case supplies oil to the appropriate side of the piston contained in the CSU, which is connected to your central contact of a switch unit. So you can actually have a hand control lever on what's called a rack and pinion. Again, I'll use the cars as an example. Your steering wheel in a car will have some sort of mechanism like this, where a little gear on the bottom of your steering wheel goes down a rod to a rack. We call that a rack and pinion, the pinion being on your steering wheel. In this case, this is the hand controller from the pilot. A little pinion there on the rack. As he turns that back and forward, that will go up or that will go down, which will direct or not direct oil through to the system, and then which will increase the mechanism for your controller. Moving the piston, your direction completes a circuit to the pitch change motor, which allows you to change your propeller blades to the required angle. Some multi-engine aircraft, another type of electrical control system is used. Single propeller pitch lever controls the speed as master electric motor, which is used as a reference for engine speed, and that drives the stator of a contactor for each unit. Each engine drives an alternator. Alternator provides your power, which supplies a 3-phase alternating current to the stator windings of your appropriate contactor, and that frequency you might want to highlight is proportional to engine speed. So maybe worth highlighting that one. During operation, a magnetic field is built up around the stator with a phase rotation opposite the stator. Again, you'll have covered this in Module 3 and a little bit in physics as well. But the stator speed and alternating speed are the same. The magnetic field will therefore be stationary. So if it's stationary, alternating speed will result in rotation of the magnetic field. The direction of rotation depends on whether the alternator is rotating faster or slower than the actual stator. So therefore, rotation magnetic field influences a concentric rotor, which rotates it and closes a pair of contacts, completes the circuit, and the appropriate windings in the propeller change motor. In other words, what it's saying is the change in magnetic field will give the motor, will move it to whichever direction. Sometimes switches are normally provided to enable pitch changes and feathering to be carried out manually if we don't want to do it automatically. Okay. Right, that was just finishing that bit. Right, guys, that's past now. That's coming back in about 20 minutes. We're going to finish off on. Don't go too far today. Yeah, we'll just finish the section one off. So Let's go for a break for the moment. Come back again about 20 minutes. Okay, and we'll finish off today once we do a little bit of recap. All right, so see you in about 20 minutes, guys.
Okay.
Let's see, where are we? How much we got there from there is there's quite a lot of technical bit. This next part is it's straightforward, but we'll take our time with it if that makes sense. There's quite a lot to it. I'll not try and go too far in. We'll see how we get on today anyway. That electrical part we've just done, basically we have an electrical type mechanism. It can increase or decrease the pressure to the propeller depending on the magnetic wave and so on and so on. It won't go that deep in the exam. Just be aware of the types of movement or the types of mechanism we can use to actually turn the propeller blades, okay? The questions aren't usually not as deep as that last page. Just be aware of the principle of each type of one. From single acting, double acting, electric motors, and a basic on electric motor principle, okay? So I'll keep you, don't worry too much about it. All right, let's see, we've got back 8 back in, we're missing 2, hopefully back in shortly. So same again, we'll do about 45 minutes, maybe an hour maximum, and see where we are, and we'll finish off there for this today. Right, so we'll move on now to constant speed units, okay, and what's involved in those. So CSUs, or constant speed units, are usually fitted to piston engine aircraft with single acting propellers. Again, looks like a PCU, okay, but CSU are for piston ones, but it works in a very, very same sort of principle. And again, typical single acting propeller CSU operation is the major components in a single acting CSU are pilot's speed input lever, a control spring, just like we saw before, centrifugal flyweights, throw slide governor, so basically a valve which increases or decreases how much pressure goes away. Need an oil pump to help it actually provide the oil flow to provide the pressure in the system. And again, a non-feathering accumulator or pump as well. And with that, we need a non-return valve and also some sort of relief valve, so don't overpressurize it and the oil goes one way only. Okay. And as usual, we need some oil supply galleries and tubes. Okay, somewhere to actually direct this oil to go and maneuver the propeller blades. So usually located, just as we saw before, on the reduction gearbox casing. Again, that could be a typical sort of question might come across an exam. Where would you find a CSU or a PCU? It would be on the reduction gearbox casing. So worth highlighting. So just to reinforce that, there it is again. Okay, just exactly the same as we've seen before. They look very similar to the PCUs and they work in the same sort of principle. So, any tendency for the engine RPM to change from the selected value is again automatically controlled by PCU or CSU. The constant speed operation of the propeller again therefore is determined by position of your PCU, your CSU. Slide valve. Now, the slide valve that proportions that amount of oil pressure is controlled by the engine RPM and what's called the governor weights, and you'll see this in the diagram shortly. The pilot's throttle position, again, is like via the rack and pinion mechanism we saw on the electrical type thing, on the governor spring. And in the event of engine speed being different between the pilot's throttle selection and the governor weights will move a slide up or down. Basically, it's a valve that moves up and down inside the governor, which allows more or less oil, which will then increase or decrease the angle of the blades accordingly. It's quite a basic system. It looks more complicated than what it is, but it's quite a basic system. So when the slide valve is in the central position, it seals off the oil feeds to propeller operating piston, and therefore you could almost call it a hydraulic lock. It stops the propeller in that certain angle where it is. Everything's happy, the engine speed's happy, propeller angle's happy. We're in effectively in a hydraulic lock, so it keeps it in that position. Somebody coming in. That's Manny. Okay. Right, so if the engine speed drops below the RPM for which the CSU is set, we call this condition underspeeding. Strange enough, if it's low RPM, we are in an underspeeding condition. And the rotational force on engine-driven CSU flyweights becomes less. Now these flyweights move out or in depending on centrifugal force, hence what I call centrifugal flyweights, and we'll show that shortly. So in an underspeed position, I'm just at the top first actually, there's your rack and pinion by the pilot's lever. Okay, so a little pinion there, and there's the rack, which is a geared teeth, so we'll move this valve up or down accordingly. Here are your centrifugal flyweights, which will, as there's the flyweights there, if there's my thumb and finger, the flyweights, the faster they're getting spun round, going round and round, we'll move the flyweights that way, yeah? So where my thumbs are would be these parts here. So the more these move due to centrifugal force, the more that the thumb parts move up, which will move this valve up accordingly. Now, when engine speed drops below RPM, obviously the flyweights are going to be, so that way, they're going to be further in, as it is in the diagram. And this is what we call the underspeed condition. Okay, just in the diagram, just for your convenience, there's your oil pump. Okay, there's a little relief valve or turn valve. And okay, and the valve in here will direct oil accordingly to the pressure on the cylinder. Okay, so we'll see how this moves. We connect it all together. The oil will be directed. Now in this case, on a single acting one, okay, we've got the oil coming through the tube. Oil pressure builds up in the underspeed condition. So which way is it moving? Is it moving to the coarse position? You can see it anyway here, or the fine position? The oil pressure builds up, more flow, more pressure, moves this grey piston back the way, which moves it into the fine position, which will then allow that propeller to go faster. So we were in an underspeeding condition. Okay, so pressure build up and eventually move into a finer position to bring the propeller faster to get back to a neutral position. So just in case the engine speed drops, in other words, it could be in a climb. Okay, we've got a angle of attack on the blade angle. The aircraft will go so far, then it will start to struggle because it can't get enough forward momentum. We need more torque, so we need to decrease angle. So this will be sensed by the flyweights. Flyweights will say, right, okay, let's move the valve down, let's open the oil supply, let's allow oil supply to go through the tube, to go and move the piston backwards, which will move into fine position, which will allow the propeller to go faster. That's all it's doing. It's basically more oil, no oil, and that's it. Okay, on a single acting one. All down to the flyweights. Okay, where they're going in the way for slow speed or out the way for high speed. So this is what we call the underspeeding condition. So flyweights are basically facing in the way. Constant speed, this allows the control spring to move the control slide valve down, which allows oil from the gear type pump to flow through passages in the propeller and then move the rear pistons. This in turn decreases the blade angle and permits the RPM to rise and return to what we call the on-speed condition. In other words, we're happy now. We're at on speed, we're where we should be, the right speed for the engine power. So we went from an underspeed condition to what is now called the on-speed condition. Okay, so there we go. On-speed condition. The flyweights are now level. They are happy. They're not underweight. They're not too fast. They're now sitting spot on. They're now happy. We've got the right position for the power of the engine and the position of the blade angle. So what's happened now is the flyweights have gone from underspeed. They've come up a bit. They've lifted the valve up, which is now closed off, or the supply to the piston, which would be down here. So there's no more oil going to the piston, which means the blades will not move. It's in a happy position. It's on speed condition. Okay. On speed condition, it's all happy. Under speed condition, so you can see a difference in the flyweights. So the valve drops down due to spring pressure. Spring is pushing the valve down. We've allowed the oil to flow to the piston, which will be down here. And then we get what's called the opposite of that, the overspeed condition. We're going too fast. So if we're going too fast, this time the flyweights now go from underspeed to on speed to overspeed. So my thumbs are now pushing up on the valve here against the spring pressure. Now what that does, that instead of closing the valve like it was in the on-speed condition, down here, sorry, it will open it and allow the oil pressure to drain away and allow to coarsen the blade. Now if we coarsen the blade, we increase the blade angle, that puts more strain on the engine, which will slow the RPM down, so we don't get to an overspeed condition. Again, once that senses the position of the blades, it will settle down and it will move from the overspeed condition back down to the on-speed condition. Okay, so you have three main positions: on-speed, underspeed, overspeed. Okay, we'll run through it quickly again. So let's say we're just flying straight and level, set RPM, nothing's changing. We're going to be in an on-speed condition. Flyweights are neutral, spring pressure is neutral, the valve has blocked off the oil supply to the piston. So the piston can't drain and the piston can't have any more oil. So it's in a hydraulic locking effect. It's happy. Let's start climbing. We maintain the same angle of attack as we're climbing for the blades. Well, it's going to start slowing down, yeah? We're going to get to a point where, no, we're struggling now. The engine RPM starting to slow down, starting to struggle. So the centrifugal flyweights will start falling back in because we're going too slow. That will allow oil pressure to come out and go to the front of the piston. Push the piston back into a finer position, which will allow it to speed up. Potentially, it might overspin a little bit. It might get to overspeed condition, and then it will settle back down into good old on-speed condition. Okay. Everybody following so far? Anybody totally lost?
No.
No, it's quite as simple. It's just an on, off, or on condition. That's all it is. We either supply oil pressure to push against the piston, or we allow the oil pressure to drain off, which is in the case of the overspeed condition. So if oil pressure drains off the front of the piston, the spring pressure takes over and puts the blades into a feather type condition. Quite a simple system. And all it is using centrifugal force to move these weights, either up the way for overspeed, or the slower the speed, the more they come in, or sit bang on where they're nice and happy. Okay, that is pretty much it for that one. Okay, check the diagrams. We've got nice big diagrams from page 24, 25, and 26. All right, hopefully that makes sense there. Again, I would love to get these animated. I'll try my best at some point. Okay, ground operation check for piston engines. The following checks on the operation of the propeller and the CSU must be made before the first flight, because we need to make sure the governor is actually working, these flyweights are working, etc. And if you've maybe replaced one or both of the items. So if you change one of both items, the propeller or the CSU, you must do a ground check and make sure these are actually working. No point going flying, not working, because that could cause a bit of a problem. Now, with all relevant safety precautions, obviously pre-flight or pre-ground run check, should say, and RPM lever in the maximum position. So if it's in the maximum position, it's in the fine pitch. Okay. Remember, if we brought it back the way, that'll be in the coarse pitch. So in the maximum position is the fine pitch. We'll start the engine up, and we'll warm up in accordance to manufacturer's instruction, usually for a couple of minutes or so, 2-3 minutes. We're going to carry what's called a dead, alive, and a single ignition check. Just be aware of those types at the moment. It's a way of checking the magnetos in here actually sparking when they should be sparking, and likewise they should be sparking when they're not sparking. Okay, especially if you've got a twin type system. Okay. We'll basically switch one and off at the same time. We'll notice a drop in RPM or not a drop in RPM, and then likewise, if we switch them both off, the engine should cut out. But what we do before the engine totally cuts out, we switch them back on again, okay, and it should come back in. It's just checking magnetos. For the moment, just be aware of those checks. If you're doing module 16 piston engines, then we go into it far more in depth. But for the moment, just be aware that's what you would carry out. they wouldn't be asked any information in a question on that. Exercise the propeller. Well, if we're going to start the engine up, we're going to warm the engine up. We get the engine nice and warm, or the oil nice and warm. So we open the throttle and ensure that manifold pressure is not exceeded. Again, you have a gauge in your cockpit showing your manifold pressure as well as RPM. We don't want to exceed manifold pressure. So the pressure in the pipes, you can potentially blow up, and the pilot needs to make a note of that when they're flying at altitude and coming down, that they do not exceed manifold pressure, because it can cause a lot of damage. So once that's happy, one of the most common methods of exercising propeller is simply operate from maximum to minimum. So from fine to coarse position, and then minimum to maximum. And do that a number of times. And why are you doing that? You're warming up the system. You're getting the warm oil through there. You're exercising the rotation of the propeller blades, and it also helps get rid of any air in the system. If there's any, it helps bleed the system out. Okay, so max to minimum, warms the oil up, bleeds in the air in the system, and last thing you want to go flying, and you've got air in the oil system, and the propeller blade starts sort of jerking, all of its own. It needs to be bled, just like a hydraulic system. Okay. As I said there, yeah, expel the air, the maiden oil, and suck it warm oil to the working parts of the compressor. Keep it nice and warmed up, and it should be working fine. If you find that when you're exercising back and forward and the propeller is sort of jerking or twitchy, you've probably still got air in the system. So just do it as many times, but do it progressively. Don't go back and forward, back and forward, back and forward. Nice and smooth operation, backwards and forwards. Let it stabilize, back up again, back down, and do it as many times as you deem fit, to the point where you're happy that it is warmed up and any air is out of the system. Again, when you're doing that, observe the RPM of the engine, exercise propeller control, ensuring that when it's moved from maximum to minimum, the RPM decreases, and when moved from minimum to maximum, it does increase by the correct amount. Not too much and not too little. Again, you have to check your figures against your relevant engine data. Roughly though, approximately 400 RPMs to 600 RPM, depending on the model. Okay, so there's some sort of things you might make a note of. Roughly 400 to 600 RPM. All changes in RPM should be smooth, so we don't want to see the levers going back and forward like a crazy thing. Nice smooth operation, backwards and forwards, nice and steady, especially on the ground, because it can cause problems otherwise. Constant speed check, adjust the throttle to give cruise manifold pressure, and then move the propeller lever into the governing range. So the governor is going to be controlling, yeah? It's going to be maintaining the pitch of the propeller. You should see a reduction in of RPM, and approximately 200 RPM should be noted. And close the throttle a small amount, and there should be no undue variation in the engine RPM. Because it's a constant speed check, it should be twitching the propeller to compensate within the governor range. And that shows that change in engine power are followed by corresponding propeller pitch. In other words, we're getting constant speeding. If you see a change in RPM, it means it could be a potentially problem with the governor. Okay. So open and close the throttle, small amount, and there should be no undue variation. You might get a minimal amount, but there should be no obvious variations. Then set the propeller lever to the maximum RPM position, and again, check your reference RPM under static conditions in accordance with your maintenance manual. Feathering check, so we want to make sure it goes in a fair position. Should there be a failure of the engine in flight. Oops, that's out of sync there. Car rate of feathering and unfeathering operation. After the ground run has been completed, again, check the system for any oil leaks. It shouldn't be there. You've maybe changed the components, so you would do a leak check anyway. And when you're carrying out this run, we're on the ground, so again, you've got to think of temperature of the engine. Only run it as long as deemed necessary. Don't run there for ages. Gas turbine engines, they can run as long as they want, but certainly piston engines, propeller engines, can get warm very quickly. So only run it for as long as necessary. Oh, excuse me. So a typical double octane propeller CSU operation. That will come to the next. Okay, just double checking, make sure it happened there. Right, this is where it changes a little bit now. Now, we looked at a single acting one, so we can increase oil pressure to the front of the piston to move the piston back into a fine position, and likewise, if it decreases the oil pressure, the spring takes over and moves into a fair position. Now we're looking at a double acting one, which flips it back to front, just to make it confusing. So on a double acting propeller fitted to piston engines, the centrifugal force acting on a rotating blade has to be overcome using governor oil pressure from your CSU, which is roughly 350 psi. To rotate the blade into the fine pitch engine position, oil pressure is assisted by the CTM, will be sufficient, roughly 60 psi. Now, as RPM drops, the flyweights will move inwards, again, assisted by the governor spring, so the spring's trying to push these down anyway, but as RPM drops, the flyweights come down, like we saw before, nothing changes there. That will allow the lower control valve in that position, that will close off the governor pump supply and allow the oil trapped in the front of the piston to drain back to tank, or the sump in this case. In the same movement, the control valve will open up and engine oil supply to the rear of the piston, which will push the piston forward and rotate the blades to a finer pitch. I'm going to have to, I think I'll highlight those ones a bit better. Okay, so basically, we're going to get oil pressure behind the piston. Piston will come forward and put the propellers into a finer pitch. Why they didn't just switch the supplies round to keep the same as a single acting? That's just the designers being designers. So let's have a look. Under speed condition, there's your flyweights. Now, I don't have the flyweights moving, unfortunately, in this one, so just bear with it. Flyweights, in this case, that's looking like a non-speed condition. Picture the flyweights in the way. So the valve is down, all right. We've got oil supply in here, and we've got an oil supply in here, because remember, we've got oil supply both sides. There's your pump supplying the pressure, all right. So this time the valve is going to move down. So the valve's going to go down. It's going to move the piston across this way, which will move it into the fine position, all right. As the blade decreases, the load on the propeller decreases, which is good, which allows the engine to turn the propeller faster, therefore allowing the RPM to increase, and the setting originally set to the RPM lever will go back to, again, the on-speed condition, where it's basically a hydraulic lock. Increase in RPM will affect the flyweights by the centrifugal force, and that will pull the control valve back upwards, exactly the same as a single acting one, until the control valve blocks off all oil passages, therefore maintain the RPM set. In other words, we will go into a hydraulic lock. Overspeed condition, well, it's the opposite way around, isn't it? When the RPM goes too fast, above the set by the RPM lever, in other words, got too fine a pitch going on, the flyweights will again move outwards, like we saw before in the single acting. Due to the increased centrifugal force, that pulls the control valve upwards against the spring pressure. Open the governor oil supply to the front of the piston this time, and that will allow it to drain away from the rear of the piston. Okay, so I said I don't have the flyweights moving, unfortunately. I've just got arrows. I need some more money to do some graphics on this one. So this time the valve moves up the way. What you can see now is there's a greater pressure in this side, so the piston, which was here before, has now moved. Sorry, I'll move there. It's now moved back the way, which is in turn moving the propeller blades into a coarser position. So we're going too fast before, move the blades into coarser, that will put more load on the propeller, which will slow the engine down. Then once the pressure builds up or senses it, the centrifugal flyweights will slow down, and they'll go from an overspeed condition, back into a non-speed condition. Okay. So increase in blade angle, increase the load, reduce RPM, yeah, happy with that. And as the RPM reduces, governor spring pressure will move the control valve down, resetting the valve back again to your on-speed condition. When the RPM reaches that set by the RPM lever, flyweights move the balance against the control spring. It places the control valve in a neutral position, which blocks off both ports, either to the front of the piston or to the back of the piston. So there's no oil flow There's no oil draining away from either side. It is now locked in position. Basically, like I said before, a hydraulic lock type scenario. Back to on-speed condition. Okay, so there we go. That's represented by the yellow here. So we've got equal pressure that side, equal pressure that side, and as you can see there, the port is blocked off on both input and output. Yeah. Now if you think of design, if you just flip that about, you could have the piston moving the same way as a single acting, but this is the way they've designed it, just to be different. Okay. So no oil flow from that side, no oil flow from that side. In other words, the piston will not move either way, it's hydraulically locked. We're then back to the on-speed condition. So it's similar to the single acting. Only difference is we're using oil pressure on both sides of the piston, this piston here, yeah? So we either push the piston forward or push the piston back. And remember, the difference between a single acting and a double acting is when the piston goes forward on a single acting, it's feathering. But when the piston goes forward on a double acting, it's going to a finer position, just to be different, confuse you. Okay, that's the designers for you. Okay, how we feeling with that one? Not too bad. Brains fried yet? Everybody happy? It's all quiet. Anybody confused? Please let me know. No, silence is golden. Silence is golden. Okay. So there's your on-the-speed condition again. All right. You can see there the valve has been lifted up. All right. So we've got open, so it's sitting there, the valve, sorry, the flight is go in the way, the valve is open, so we can get fuel pressure, shut up, oil pressure, okay, to speed up, so it pushes the piston that way, goes to fine position. So there you go, there's my no expense pair graphics. All right, under speed, fine position, over speed, we're going too fast, so this time it's the top oil supply which runs through the tube, pushes it into the piston, pushes it backward, makes it a courser. And then when we're all happy, we'll end up in a non-speed condition. Okay. So if you look at the valve positions there, over speed, it's been lifted up, this line's open. Under speed, it's this line that's open at the bottom. So the oil pressure can get round and up into that side. I need to change the colour there, it was red. Okay. Finally, hydraulic lock. Both ports are closed, so oil can't escape or enter the piston. It'll sit there until the situation changes again, until they're happy for next time. Okay, so there we go. So turbo operation PCU, again, PCU is similar to CSU, but again, usually used with the turboprop engines. Usually one of the main differences is that PCU has a single lever, okay, which is connected to both the PCU and also the fuel control unit of the engine. So propeller control unit and the fuel control unit. So it saves a bit of hassle. Instead of having two levers to work about with, we just have the one. Takes the load off the pilot. RPM and fuel flow are selected together, enabling the engine to overcome the combined inertia of propeller and compressor, which impairs engine acceleration. Single power lever selects the propeller RPM for the particular power setting, and the PCU is usually mounted on and driven by the engine, and drive operates a spur gear pump which boosts the engine oil pressure to the system operating pressure. Maximum system pressure, again governed by a relief valve. Again, in case that pressure builds up too much, the relief valve will open and relieve that pressure. Provides an idling circuit for the pump when the control valve is in neutral, because if we don't have a pressure relief valve, the pump will keep flow will keep going. If it goes nowhere to go, it will just explode. So by having the relief valve, it just lets the high pressure go back to the low pressure and just keep recirculating, just like the heart inside you. The heart pumps your blood out, high pressure, and it comes back in the low pressure. Yeah, just back and forward. Drive gears rotate the governor weights, which tend to fly outwards, again, like we saw before. And the governor weights are linked this time to the control valve, same as we saw before. move the fly upwards as they fly outwards. So linkage from the power lever loads the governor, or speeder ring, which tries to push the control valve downwards. And a further connection to your HP cock. The HP fuel cock, excuse me, is the one that supplies the fuel to start your engine. You'll cover again some of this in module 15. We've also got an LP cock, a low pressure cock, which is the fuel supply from your aircraft to your engine. But the high pressure or HP cock is the one that supplies it to your actual engine. But having it all combined in the same lever makes things far easier. A solenoid valve, which is an electrically operated solenoid valve, directs oil pressure to lift the control valve for automatic feathering and withdraw the pitch lock to move into what are called ground operating range. So again, it's very similar. We've just got a few levers. Basically, inside here is the very same principle of what we just saw before, except we've got a few more control levers. Okay, we've got a feathering control, which manually supersedes anything going on here, which will lift the valve up. And we've got a max and min RPM control, basically your power control. I have a valveless solenoid, constant speed maintain, and there's your flyweights again. Now they'll do their job automatically. You've got your coarse line, you've got your fine line, and then your oil pump supply and oil return. So depending on the position of this valve, will you supply oil to the coarse side, the fine side, or return it all back to return. Okay. Excuse me. So PC operation of flight. A decrease in forward speed, for example, as an aircraft is climbing. So we're going to slow down. It's going to be more strain on the propeller. Angle of attack increases. Yeah, that makes sense. Propeller torque increases. Yeah, we've got quite a coarse pitch, so the torque is going to be quite high. PCU decreases. Decrease in centrifugal force to govern weights allows the speeder ring to lower the control valve. So we've gone from on speed, now we're going to a low speed condition, just like we saw before in the CSU. So decrease, oil pressure is directed to the flight fine position, or the fine position, sorry. So supply will go, and that will allow the piston to go to the front, to go to the fine position, which will allow the engine to speed up. Coarse pitch oil has to get rid of, so we return it back to inlet side of the pump. And the blade angle is therefore decreased, which means it can cut through there easier, which then means it can speed up. Propeller torque is then restored. RPM is now selected value, but with a finer blade angle. Yeah, as we're climbing, we can't have it in fifth gear like a car. We need to come down a gear in a car. If you're going up a hill, you need to come down to second, third, maybe first. So this is the equivalent of gearing. We just change the blade angle, depending on what it's a PCU system or a CSU system, or whichever, okay? It all does the same thing. An increase in forward speed. Okay, angle of attack decreases. So what's going to happen to the angle of attack? Angle of attack decreases. That means the propeller is going to go faster. We need to slow it down. We need to slow it down by increasing the angle of attack. So propeller torque decreases. RPM increases, which is not what we want. Increased centrifugal force will then spin the flyweights out the way, lift the valve up. Pressure is then directed to the coarse side. Okay, so in other words, it's going to go to the front of the piston, push the piston back, which will then turn the propeller blades to the coarse position, and then put more load on the propeller, which will slow the RPM down. Okay. Fine pitch oil is returned to the pump inlets, does the opposite of what we saw before. Blade angle is increased, so we've got a coarser pitch. Propeller torque is restored, and we're all happy. It's a happy thing, a National Happy Week. RPM is now set at selected value, but with a coarser blade angle. So the aircraft's going faster. The blade angle has increased to match the forward speed, which maintains the RPM in the engine. That's what it's all about, maintaining the RPM selected. Okay. That's sinking a little minute. What are we doing for time? See a quick test. Okay, I'll just have a look to see how far we're getting today. We're too far. Oh, okay, great. Yeah, we'll probably got to. Let's double check. Right, we'll do section 2. Won't much further than that one today. We'll leave the rest for Monday. So we'll just yeah, let's go for a quick break and we'll finish off with the last section for today. Okay, so come back about 1:45. Just a little quick break there. Come back at 1:45. We'll finish off section 2, and that'll do for today. Okay, because that's quite a lot to take in before the weekend. So hopefully your heads aren't going like that. Okay, so come back in about 15 minutes, guys. Okay.
All right.
Okay.
Straight away, especially when the engine isn't running. Okay, so centrifugal force will spin those out of the way normally, but for a ground operation, you want to manually move the blades for whatever reason, for maintenance, or even to take the propeller blade off. We have to use special tools. Again, some installation, the ground fine pitch stop is removable to facilitate a reverse pitch operation. So that's a ground fine pitch stop. The flight fine pitch stop, very similar. We've got FFP. Again, this is a removable mechanical stop, and when engaged in the lock position, does not prevent the blades from coarsening, but does prevent them, once they are past the stop, from moving back into what we just saw, the ground fine position. We don't want it to go in ground fine position. We want to go to minimum flight position, maybe 2-4 degrees, something like that, and then operate as normal through normal flight conditions. So basically, we come out of ground fine pitch stop, we go into normal flight conditions, we can bring the propeller back to flight fine, which is the minimum requirement for normal thrust. Stop must always be engaged in flight to ensure that windmilling, drag, and engine speed does not become excessive under any conditions. And when it's necessary for propeller pitch to fine off to the GFP stop, set in the FFP, a lot of FFs and Ps going on, a lot of abbreviations, can be removed by applying hydraulic oil pressure to the stop locking mechanism itself. So hydraulic oil pressure is controlled by a lock withdrawal solenoid, so electrically operated in your PCU. And the method of completing an electrical circuit to energize the solenoid varies with different types of aircraft, obviously. Again, example has been weight on wheels, maximum forward speed, and the RPM of the engine at the time. So it will only activate when those conditions are met accordingly. So there's a basic flight fine pitch stop, and there's your lock there. Okay. Now, at the moment, flight fine pitch stop, it means that the piston, there's your propeller blade. Okay. When that piston moves back and forward, it will only go as far as that stop there. So in other words, it's a normal, who's just come in? Saroj, okay. It's a normal operating range. And this part here to that part there, the piston can only move that far. All right. Which is all good. That maintains we can fly as normal, we can come to flight fine, we can go to that course, it doesn't matter. It can only go as far as that stop there. Okay. We'll have some sort of circuit where we can manually feather, depending on RPM, depending on the position of the weights, depending on the position of the valve, will allow oil pressure to move back and forward as normal. But if we direct some oil pressure to here, we can actually put oil pressure in this part here and move or slide the pitch stop back down, which will allow the piston to go past into ground fine pitch. But in normal flying conditions, it will only touch that stop there. Okay. So withdrawal method selecting your flight fine position stop is simply resulting in energizing the FFP lock withdrawal solenoids. Maybe a series of circuit between the throttle levers, undercarriage micro switches, weight and wheels, emergency switch, etc. Depends on the system. Misselecting simply results in energizing the solenoids. Again, as I've said, there are micro switches and so on. Now the emergency switch would be selected to normal during engine running and flying. So in other words, we don't direct oil to the pitch stop. The mesh selecting will only be used to withdraw the stop once you've landed. In other words, you've got weight on wheels. If the normal withdrawal method was inoperative, in other words, there's maybe a fault with the micro switch on the weight and wheel switch, it's not activating, then we can manually position that. Obviously in flight you wouldn't do that. It wouldn't be energized to the relay. Solenoid circuits for all engines are made when all throttle levers are closed and at idle position. We don't want potentially having a fast engine potentially going straight into ground fine position. That would just be disastrous. Okay, it'd be far too much. The micro switch landing gear legs are closed by the weight of the aircraft. In other words, your weight on wheel switch. And the emergency switch is at normal. Okay, so probably worth highlighting those in your book. Let's have a look. Yeah. Okay. Usually on the FFP stop withdrawal, there'll be a light in the cockpit, allows you to know what's actually activated, indicates whether all the FFP stops are locked or withdrawn. If the light's on, that means any light comes on the cockpit is a warning. It could be a severe warning or just a caution. But if light comes on, that tells you or the pilot that the actual stop, that little red part in the diagram, is actually out of the way. In other words, we can now move the propeller to the ground fine position. No light, it means it's just in the normal flight range. It doesn't matter. So light out, the stop is up, and we can go in flight range. So light on, it's alerting us that yes, I can go into the ground fine position if required, providing I'm at low throttle settings. I've got my wheels down, I'm not flying. We don't want to be doing it when we're flying, certainly. Okay, so probably worth highlighting the light on, stop out, light out, stop locked. Okay. So let's have a little look. Oops. There's a little diagram. Again, this is circuits. We've got a pitch lock operating solver, we've got a piston lock operating solver, we've got feather control, we've got your maximum throttle position. This is a combination of everything going to your on-speed condition. On-speed condition, you can see there that we're happy. The pitch change mechanism is all happy. The flight fine stop is out at the moment. So we can move back to fine position and normal position. The valve here is locked off, so we're in hydraulic balance. There's no pressure at the front. Well, there's oil in there, but the pressure in the front of the piston, pressure in the back is all good. Okay, all happy. Right, so this is where the flight fine pitch stop is lowered. What's happened? We've directed some oil. In fact, I'll go back to the previous diagram. You can see at the moment, the stop lock is out. Okay, so if the piston was to move backwards, it would stop against the actual lock. It wouldn't go any further. Okay, so normal on-speed flight condition. Fine, of course, as required. But it can only go as far back, this part here, to the top of the lock. So, in fact, I'll go back again, sorry. The oil, at the moment, there's no oil supply in here. Okay, we've not operated the pitch lowering valve. So there's no oil pressure there. Okay, we've not selected it from whichever version. We've not supplied oil, so there's no pressure in the system, which will move this red valve back, which allows the lock to lower. So in the next diagram, this time we've supplied some oil pressure into this cavity here, which has moved this cylinder back, which allows the locks, okay, these are both operate at the same time, to lower. That means that we can now move the piston back to the ground fine pitch position. So instead of going just to here, which would be the flight fine position, we can now move this all the way back to the ground fine position once we're at lower speed and weight on wheels. Okay, so there we go. A little animation just to show you where it's going. So we've gone past the flight fine pitch stop, which was the blue lock here, because we put pressure in the system, moved this valve back. Now you can see as well these little round circles here. I don't think you see it very well in the book. Let's double check where it is. Yeah, page 36. That's the spring. So the spring is always pushing this cylinder forward normally when there's no oil pressure in here. In other words, if that's pushed forward, that will maintain the lock up out the way once it's in flight fine position. But at the moment, we've changed that. We've put pressure in there, moved the red cylinder back, which allows the locks to drop, which allows your propeller to go back into ground fine position. Oh, excuse me. There you go. So we've put pressure in, moved this on the back, the locks are out the way now, allows the piston to go fully back to your ground fine position, and that will stay in that position until we change something. Okay. We've got an on-return valve there as well, which will lock it in position. once we change that, we can relieve the pressure, which will allow it to go back away once we move that forward, once required for starting up or so. Okay. Everybody okay with the ground find position and the flight find position? Everybody okay with that one? Silence is good. Right, we'll finish off this last part. We've got a typical electro-hydraulic stop. Again, depends on design where applicable. So, in the event of a failure in flight, which allows the propeller to move below the flight find position, which is not very good, a signal from propeller blade angle hub switch will automatically initiate a coarsening system. In other words, we don't want to be able to ground flight position when we're flying, because that's going to be quite disastrous. We need to bring it a bit coarser. Now the propeller, if that happens, it will help coarsen the blade off automatically. Propeller will coarsen until the hub switch again breaks the circuit. Now, unless something changes, what will happen is, unless power of the airspeed is sufficient to maintain the pitch above the hub switch, the propeller will what we call hunting over a small angle edge. In other words, what will happen, the blade will go back and forward, back and forward, back and forward, back and forward. So it'll be slowing up, speeding up, slow down, speed up, slow down, speed up, slow down, speed up. We get a hunting effect. It lets us know that something's not quite right, and also the pilot will have to react to that. So to indicate this hunting, the propeller below stop light, one for each propeller will flash on and off, respectively, as the blade moves back and forward. So whenever the flight find pitch stop withdrawal system is energized, the coarsening system is cancelled, but the propeller below stop light would be on if the propeller pitch was lower than the hub switch setting. And this is what it is here. It's a little micro switch. So we've got a hub switch. So if it's gone below flight find position when it shouldn't have done, okay, that position will actually indicate there on a micro switch to let us know that that has happened when it shouldn't have happened. Okay. De-energize on the ground, obviously, but it's in flight conditions that would energize. So in the flight, the propeller commences to fine off below the flight find position. The hub switch fitted to the propeller's blade completes the circuit and to the piston valve lift, pitch coarsening solenoid in your PCU. When the solenoid is energized, the PCU oil is directed up from the pump to the top of the PCU slide valve via the solenoid. The slide valve will be lifted, thereby directing oil to increase the pitch, causing propeller to coarsen. So in other words, we'll get more load on the propeller. And as the propeller coarsens, the solenoid will then be de-energized, closing the oil line to the top of the PCU valve. The valve will then move down again, causing the propeller to fine off. And that sequence will go back and forward repeatedly, causing the propeller to hunt over a small, not massive amount, just a little bit here and there, so it'll be a small angular range. Okay, and what's happened there? When a low withdrawal solenoid is energized, excuse me, the PCU pump pressure is supplied to the third line as follows. It's worthwhile, though I'm going through it in the PowerPoint, take your time to read the procedure through in the book until you get it clear in your head as well. So, PCU pump to flight find pitch lock withdrawal solenoid is activated. Yep. Stop withdrawal solenoid to the third oil line, which is the one that pushes a little cylinder. The third oil line valve opens. Your PCU pump pressure is then directed to the pitch lock piston and propeller. The pitch lock piston moves rearward and allows the propeller operating piston to close and the spring collet and move towards the ground find position. Okay. So there's a pitch lock. Hydraulic safety valve is the one I mentioned earlier. This one here is usually incorporated into the fine pitch line. It is an emergency stop, and that will help prevent a propeller moving to a finer pitch due to failure of the oil supply from the PCU. So that basically does a hydraulic lock. It stops it going to a finer position in case there's a failure. Okay, so that basically puts a hydraulic on there, stops this piston here from moving backwards, even if there was pressure in there. It just goes hydraulic lock. Okay, that's it there. With no pressure acting on the face of the valve, the hydraulic safety stop will hold the propeller's pitch at the angle at which the pressure fails. So it'll stay in that position. So rather some sort of angle than no angle at all. It won't be ideal, but better something than nothing. That will block the coarse pitch oil line from returning and prevent the propeller fining off. Okay, so it will stop being a drag, rather a bit coarser than too fine. We can sort of just about live with that. The ball valve, however, will allow coarse pitch and supply to pass to pitch change pistons so that the feather facility is not impaired. We definitely don't want to go into a fine position if we've got a problem, but we do want it to go to a feather position if there's a problem. We can live with that one. We won't cause a drag in the aircraft. So it's a safety in effect. We stop it from being fining. We can feather it off in emergency. Okay, that's about where I'm going to stop for today. We'll start with section 3 tomorrow. I won't be here tomorrow. You guys are working. I'm not working. But we'll be back in on Monday, starting with section 3, page 39. So what I'd like you to do, hopefully Sanjeev has been in touch with you, or you can get the questions I've supplied to him. The questions in the book, the 2 sets of questions, if you can complete them for Monday, if you haven't done so already, and we'll go through those first thing on Monday morning. Any questions you have about anything at all, please make a note of, and you can pass them on to myself, and we'll quickly go through Monday, and then we'll see where we are. We've got how many pages left now? About 8 odd pages or so, which we should get through quite well on Monday. So by the latest, we'll definitely finish book 2 by Tuesday morning, maybe just before lunchtime, to give us a bit of revision recap as required in the afternoon, and your last chance questions before you go for exam. Any questions so far, guys?
No.
All happy? Anybody really confused? Don't admit it.
Yeah.
No. All happy. All quality guys. Yeah. No. If you get stuck in any part, just highlight it, make a note of it in the book, and let me know Monday morning once we go through the questions that are in the book. Okay. But if you don't have any questions, I can't give you answers. Well, for those who are working tomorrow, enjoy your work. Hopefully it doesn't work too hard. Have a good rest of the weekend on Sunday. Have a nice chill. And hopefully we'll see you all Monday. Make sure the connection's fine. Okay. So until then, thank you very much. Take care. Keep safe.
Okay,
keep away from
see you.
COVID-19.
Have a great
Okay.
weekend.
See you to Monday morning, same time, or Monday afternoon, your time. Okay. All the best, guys.
Okay.
Okay, thank you.
Thank you. Bye for now. Thank you.
Okay. Thank you. Bye, everyone. Bye, everyone.